Yo, I was back home by about 5:30 and then I just spent almost 30 minutes just watching some anime, One Piece, while I was having grapes as my snacks. Anyways, today I'll be answering the question that I get asked very frequently, that is, what do you actually do at my job? And before I talk about my job, my responsibilities, I want to give a slight introduction and a little background about myself. I graduated from VIT back in India in 2021 with bachelor's in mechanical engineering, and then in the same year I started pursuing my master's in mechanical engineering with concentration in design and manufacturing at Clemson University, which is in South Carolina. And then I graduated with my master's degree in 2023 May, and then I looked for a job for about 4 to 5 months, and then I got my job offer in December of 2023. And then from then I started working as mechanical engineer in a firm called Sinseal. I'm wearing the Sinseal t-shirt, which is located in New Jersey. And my job as mechanical engineer is a mix of design, analysis, fieldwork, and lot of problem solving. So let me walk you through what I typically do at my job, the skills that I actively use, and where this job of mechanical engineering falls into a bigger picture of engineering world. And maybe I'll end the video with some advice for someone who's starting their career in mechanical engineering. A big chunk of my job involves me designing custom soft face mechanical seals for different equipments like screw conveyors, augers, paddle mixers, ribbon blenders, live bottom feeders, etc. Basically any equipment that is either conveying the product or mixing the product. And by product I mean it can be chocolate powder, protein powder, cookie dough, it can be also something slurry like cement being mixed with water, or it can be human waste. Basically any equipment where without the seal the product would come out. Those are the equipments I'll be working on. And it's not the whole equipment design, it's just a small part of the equipment, a mechanical seal, a soft face mechanical seal that I'll be designing to seal the product to be within the equipment, not leak out of it. And coming to my responsibilities as mechanical engineer, I'd like to give you the workflow from start to end, so that it will be clear for you to understand what I typically do in a day. So first, customer comes to the company and submits a request for quotation, and first step as an engineer, or me or anyone from team, is basically evaluating the application that was submitted by customer, that is operating conditions or equipment and process information. And then based on the information we typically envision a preliminary design based on the information submitted, and based on the knowledge we have. It can be anything like product compatibility, or it can be something like selection of type of seal for the shaft or for the face where the product leaks from. And once we have a preliminary design in our mind, we go ahead and design it in SolidWorks. And mind you, this is the part design, and what typically happens is customer submits an equipment CAD file along with the application, and what I do as an engineer is I take my seal design, I incorporate into equipment CAD file, I create a larger assembly, and then I make sure that this seal can be installed in that particular location without any obstructions. And one of the examples I could think of is, let's say the axial space is only 5 inches. 5 inches is the axial space limited. There is a bearing after 5 inches from the equipment wall. My seal has to fit within those 5 inches. Let's say my seal is like 6 or 7 inches thick. That cannot be installed there, obviously. And this process of me assembling both seal and equipment helps me understand if there are any design limitations in terms of dimensions. And once this assembly is done, and when I realize that hey, this seal can be mounted in this location without any problem, that's when I start to create engineering drawing. And in most of the cases, the engineering drawing is customer facing engineering drawing, and this does not include any kind of tolerances or any GD&T symbols. It's just dimensional information that customer is concerned with at the time of installation. For example, the outer diameter of the seal, or the inner diameter of the seal, or the thickness of the seal for that matter, or the bolt circle, how it is being mounted, either using screws or studs. These are just the examples, not to overwhelm you with the information. But this is the drawing I typically make after assemblies, and then this drawing is sent to customer for the sake of approval. And from here, customer can either come back to us and request for few changes, or customer can approve the design saying, hey, I like the design, go ahead with the quote. And that's when the engineering drawing is sent to the quoting team. And once the quoting team receives the engineering drawing, quoting team requests for bill of materials cost from engineering, and by bill of materials cost, it's the cost to make the parts for the company. And once quoting team has these costs, quoting team has certain markups or certain profit margins which they follow for certain customers, they send the quote out to the customer based on the margins they have. And typically in most of the bigger firms, engineering role is only limited till, creating the drawing and sending the drawing to the customer. But since our company is not that big, we kind of wear multiple hats. I also sometimes help quoting team in the estimation of, bill of materials costs or raw material costs of certain seal components. And let's say once the quote is sent to the customer liked the price, and then he places an order. And that's when the engineering team, or I in this case, has to design engineering detailed drawings that needs to be released for production. And this is where skills like GD&T, tolerancing, clean engineering drawings need to be used, so that it's easy for manufacturing team to read and also, produce the part. And another big chunk of my job is testing and validation of these seals in real life. Based on business needs or, based on the industry trends, we kind of schedule few tests where I have to test that seal in real life, collect data points like temperature, wear rate, or, pressure retention, etc. And then make conclusions out of the data points I receive. And a simple example could be, let's say I ran a specific type of seal at certain RPM for 24 hours. And let's say after 24 hours, the seal temperature has reached some X degree Fahrenheit. And if I know that this X degree Fahrenheit temperature is way above than the service temperature of certain components in the seal, I know that seal will fail at that operating parameters. So I can confidently say that, hey, this seal at this RPM or this operating conditions cannot run for 24 hours. It needs to only run for, let's say, 8 hours, and then it needs to be on break for 2 hours. Those are the type of conclusions I make based on the test results I get. And I gave you a very simple example. It's not as simple as that, but yeah, I cannot talk more than this because I've signed NDA with my company. But typically testing and validation is something that goes into the bracket that I just mentioned. One of my other responsibilities also includes checking the parts for quality, and by quality I mean for dimensional accuracy. This is not something I would do daily, but maybe once a week or once in 2 weeks, where there are batch of parts produced with very tight tolerances. I just have to go check them for their dimensional accuracy, and let's say a few of them are dimensionally inaccurate. I also have to give ways to manufacturing team to make them dimensionally accurate, and one of the examples could be, let's say, this part is 1.5 inches and the part is supposed to be only 1.42 inches. What I could do is I could go ask the manufacturing engineer to face off 80 thousandths from one side. And I also have to make sure that there is nothing on this face. Let's say there are some counterbores and screw threads on this side. I don't want them facing this side. I want them to face the other side so that the counterbore depth is not affected. That way dimensional accuracy is achieved. And this example is only applicable if the manufacturing is happening in-house. Let's say manufacturing is being outsourced in some other country, China or Singapore. What we might have to do is we have to ask the abroad manufacturer to send us inspection reports of the parts before the parts are shipped. And with that inspection report in one hand and the drawing in other hand, we have to check every dimension that was measured in the inspection report falls within the tolerance range which we've given in the engineering drawing. And once this matches, we can always approve and get the part shipped. This is the typical process of quality inspection when you're particularly checking for dimensional accuracy. And now let's talk about how my role fits into a bigger area of mechanical engineering. Now my role here at Synseal as mechanical engineer is highly custom engineered focus, which means the job I'll be doing today, the design I'll be working on today, I might never repeat the same design principles again, because every equipment at customers is different, which is really good because every application I get from customer is a challenge in its own. But this is where I miss out, design engineering principles such as high volume manufacturing, where I cannot use design for injection molding, for example, because every part of our seal component is heavily customized. So we cannot do injection molding process because the cost of mold is much higher. And if we just keep on making molds for 100 different parts and just make 2 parts or 3 parts out of it, injection molding is not the right process to go with. And what I'm trying to establish is that you will find different role in this mechanical engineering domain. Let's say you're a product development engineer at Apple. One of the most important skill that you should have is knowing the design principles for injection molding or high volume manufacturing. And the reason I say that is, let's say you're in packaging team and you're designing a cap and a box for iPhone. You have to design keeping the manufacturing process in the mind, saying that, hey, the part that I'm designing should be achieved using this manufacturing process, mostly injection molding in that case. And in this product development role, that skill is something that is very frequently used. Let's say you're aerospace or aeronautical engineer. In this job, the cost of mistake is really high. So what they typically do is they have FEA softwares where you try to do finite element analysis or fatigue analysis or stress analysis or failure analysis on specific parts before you test them in real life, because the cost of failure in real life is very high. The cost in real life is basically either huge money or a human life, which is something we cannot afford. So the most important skill in this job, that is aerospace or aeronautical, would be FE analysis. I'm not saying it is the most important skill. Yes, it is important. At the same time, it is the most commonly used skill if you are in that profile. And let's say you're a manufacturing engineer, the section of skills that you'll be using most commonly would be tooling design or automation or lean principles or Six Sigma principles, something like that. So what I'm trying to say is mechanical engineering is really broad, and every company or every firm has its own flavor. So the skills you might need to master might depending on the role you're aiming or the company you're aiming to get into. And lastly, these are some of the professional pointers I wish someone told me earlier when I was starting my career. First, just don't focus on mastering the CAD software. Yes, being proficient and being master of a particular CAD software, SolidWorks, Fusion 360, Pro E, CATIA, it's all good. It's definitely good. But if you're not confident in your basic design principles or fundamental engineering principles, you will never be able to translate a design into CAD. So first focus on that, and along with that, always try to master one particular software. I've always been a SolidWorks fan from the beginning. So yes, I do know Pro E, yes, I do know CATIA, yes, I do know Fusion 360, but I'm super confident in SolidWorks and AutoCAD in comparison. And two, learn to make clean engineering drawings. These engineering drawing papers talk about you when you are not in the room. Typically what I've observed is when you're overcautious about the design, you overdefine the drawing by providing multiple dimensions which are not required, and this would confuse the heck out of the machinist or manufacturers who get the drawing. Or the other side of the coin is that you don't give them enough dimensions, you underdefine the drawing, and without the all required dimensions, the manufacturer or the machinist could never get you the part completely. So they have to come back to you to get those dimensions, which is not a good sign. And number three, communication is super important. I know you've already heard this point from your lecturers, professors, or teachers or mentors, but the reason I repeat it is I also know that as a student, you never give enough importance or time to work on the communication skills, just like I did not until I realized. So what I'm trying to say is, even if you're genius, even if you're master of 10 different skills in mechanical engineering, if you are not able to communicate the design intent to the customer or design idea to one of your colleagues, one of your engineers, your skill has basically no value. Because most of the times what happens is, in an engineering world, a problem is not solved solely by one person. It's typically an effort of team, because you might be responsible for one aspect of engineering, that is either design or manufacturing, but the other engineer has to understand what you're trying to do there. And if you don't have good communication skills, your skill has no value. And number four, this is something I picked from my experience. Whenever you join in a company as a mechanical engineer, design engineer, manufacturing engineer, anything, be it an internship or a full-time job, go and talk to people on the shop floor if you have an in-house manufacturing facility. And the reason I say that is, those people actually know how parts come in, and when you talk to them, that's when the real learning happens. And it helped me a lot. And even at this point, I go back to the shop floor and I talk to machinists about, hey, how did you manufacture this part? How did you produce this part? How did you cut this part? And when they start explaining about it, even if it's not super difficult for them to do that, you can always find most optimized way to produce that part by making small design changes, which really helps. I feel like that's where the real learning happens, and that helped me a lot. And I'm sure it would help you to some extent if you do that. Anyways, that's it for the video. Just wanted to make this video from a very long time, but it was just not on my priority list. I've been getting a lot of DMs about, hey, what do you do as mechanical engineer? A couple of comments here and there on YouTube videos as well. So thought might as well make a video on this. Anyways, I'll see you in tomorrow's vlog then. Bye bye.